Hello, my name is Stephen Trentalange from UCLA. I'm going to give you an introduction to the design, construction, and uses of the star barrel electromagnetic calorimeter. The star Bemc detector has three subsystems. First, there's BTOW, or barrel towers. These measure the total energy of electromagnetic particles with good energy resolution. However, the position resolution is not optimal. The second subsystem is the barrel shower maximum detector. This measures position resolution with optimal accuracy. However, it has lower energy resolution than the towers. It is only used for specific physics demands, and so does not run every year of star operations. Finally, provision was made for a barrel pre-shower detector. This measures the initial stages of the electromagnetic energy deposition, which gives partial discrimination between photons and electrons. It was only used in the first few years of star operations and currently is not used due to lack of physics interest. The barrel electromagnetic calorimeter is used in STAR for a wide variety of physics goals, usually for events which include a violent collision. Here I give two examples of publications which use the calorimeter as an integral part of their analysis. One identifies J size, and the other the internal structure of jets. And here I give an example of a physics topic which does not explicitly use the particles detected in the calorimeter, but uses events triggered by the calorimeters to supply a sample of events with an enhanced population of, in this case, lambda hyperons, to study the transfer of polarization from the initial proton collision to the hyperon in the final state. The original philosophy of the star detector was to provide as complete a picture of individual events as possible. To do this, we have to have the ability to detect every type of particle. Now, the star detector is blessed with a TPC, which is a great advantage as a central detector. Its main drawback is that TPCs are slow and tracks from multiple events overlap even at modest luminosities. However, they eliminate the need for a hadron calorimeter because they measure the specific ionization along the tracks. We can easily see charged kaons, protons, pions, antiprotons, heavy hadrons like deuterium, tritium, and alphas. However, we are missing some particle detection capabilities in STAR. First off, neutrons and antineutrons. Neutron counters are generally slow and/or inefficient. Neutral particles, like the K-long, K-short lambda, have only partial detection capability through their decays to charged particles in the volume of the TPC. Neutrinos have a notoriously low probability of interaction and therefore a low detection efficiency. Muons are indistinguishable from electrons in the TPC below TeV energies. Now, this has been solved by adding a detector outside of the magnet, which uses the EMC and magnet steel to filter out hadrons and leave only muons. Finally, there are the electromagnetic particles, gammas, neutral pions, which decay in 10 to the minus 16 seconds to gammas, and electrons. The neutral pions are important because there should be as many neutral pions as the average of the charged pions. Electrons are indicators of many interesting physical processes, such as the production of J size, W, and Z's. Fortunately, these last three sets of particles can be efficiently detected using electromagnetic calorimetry. First, what is calorimetry? It is a type of detector that converts the energy of a particle into a detector signal S such that S is proportional to the energy. This enjoys widespread use in particle physics and is a mature and well-understood type of detector. Calorimeters can be based on a variety of signal types, such as heat, ionization, Cherenkov radiation, or scintillation light. The advantages of calorimeters is that they can measure both charged and neutral particles. The signals can be made fast, less than 50 nanoseconds, which means that they can be digitized every beam crossing, which is, in our case, 106.5 nanoseconds. This is extremely important because it means that fast FPGAs can use these signals to form triggers for unusual processes based on the energy and topology of an event. The two most important types of triggers that we have fashioned at STAR are the Hightower and jet patch triggers. The Hightower trigger is typical of high-energy gamma, electron, neutral pion, W, or Z particles. The jet patch trigger selects events with hard processes, such as a quark collision, which results in a jet or a pair of jets. A general characteristic of calorimeters is that their performance and efficiency improves as the energy gets larger. In the TPC, for example, the fractional momentum resolution is proportional to the momentum, because you are measuring smaller and smaller sagitta for each track. In the calorimeter, though, the fractional energy resolution improves as 1 over square root of E because the deposition of energy is a Poisson process involving more and more ionization events, and thus is proportional to E. The disadvantage of a calorimeter is that the detection process is destructive. That is, once you measure it, the particle is not available for further measurements. Also, the calorimeters are heavy and use large amounts of expensive materials. I give here two references for lectures on calorimetry if you want to explore this further. This slide essentially summarizes everything we need to know to construct an electromagnetic calorimeter if we look carefully enough. First off, we notice that at some energy, typically tens of MeV for both gammas and electrons, so-called radiative processes dominate over ionization losses. What's the difference? Well, ionization losses refer to energy lost by a particle when it ionizes the material through Compton scattering or the photo effect. These losses are typically in the few MeV per gram per centimeter squared region, so they do not contribute much to slowing down particles with energies in the hundreds or thousands of MeV region. This energy, where the crossover occurs, is referred to as the critical energy. It is different for different materials, generally lower for high Z materials. In fact, above a few MeV, there are only two processes to consider. For photons, there is pair production of electrons and positrons. For electrons, there is Bemc, which produces high-energy gamma rays. These processes can be described in terms of a characteristic length in the material called the radiation length. This is the constant in the exponential decay of the energy left in the electron as a function of distance it travels in the material. The expression for a radiation length goes like A over Z squared. So high Z materials degrade electromagnetic energy more quickly than low Z materials. The radiation length is the amount of material required to reduce a high-energy electron to an energy of 37% of its original energy. As I mentioned before, the TPC largely relieves us from building a hadron calorimeter. On this slide, I show you why that is a huge advantage. On the left side is a comparison of simulations of an air shower initiated by a proton, a hadron, and the right, a photon shower of the same initial energy. You can see the right side looks reasonably well organized compared to the left. It has a beginning and an end, and is well confined to a cigar-shaped narrow column. The proton shower is wider, disorganized, and filled with fluctuations. It's difficult to see, but a significant amount of energy exits at the bottom as well. The right side gives the reason why. A hadron enters material and can initiate two different processes. Looking at the incoming negative pion, it loses only a small amount of energy to ionization, just like the TPC, until it physically hits a nucleus over a characteristic mean free path length lambda, which is many times, 20 or 30 times, the length scale for electromagnetic interactions, which you remember we call the radiation length. We see on the top right diagram that the incoming charged pion undergoes charge exchange, for example, to a neutral pion, or eta, which decays in 10 to the minus 16 seconds to 2 gamma rays. These gamma rays are immediately absorbed by the medium within a few electromagnetic radiation lengths and results in a large signal. However, the charged pion could have double charge exchange or undergone some other nuclear process such as spallation, which results in simply more high-energy charged hadrons. These charged particles are not quickly absorbed and have roughly the same probability to interact as the initial particle. This is the reason for the large fluctuations both in longitudinal and transverse shape for hadronic showers as opposed to electromagnetic showers. The electromagnetic showers, in fact, are so well ordered that they lend themselves to be well described by a toy model where the number of particles in a shower doubles with each radiation length of materials that it passes through. Here, a gamma ray turns into an electron-positron pair, and the electron or positron pair turns into an electron plus a gamma ray, etc., etc. Of course, the energy sharing is not perfect, but this crude model explains the basic ideas of electromagnetic showers. That is, after T radiation lengths, we have 2 to the T particles, with each energy E over 2 to the T. This process stops if the energy of an individual particle falls below the critical energy, EC, at which ionization losses dominate over radiative losses. The number of particles is given by the total energy divided by the critical energy, and the maximum for this process occurs at a position approximated by log of E0 over EC. In fact, a more sophisticated version of this model can be parameterized as functions like these, which are simple combinations of exponentials and power laws. The important points to bring away from these models is the maximum energy loss for the shower is in the range of 5 to 7 radiation lengths inside the material, and the depth of the shower max changes very slowly with energy, so a compact detector can fully contain a very wide range of particle energies. These toy models can be extended to multiple scattering in the transverse direction as well as development in the longitudinal direction. In this case, the shower is characterized as being contained within a transverse dimension known as the Moliere radius. This is generally related to the radiation length, but often given separately. Here's a slide which summarizes all the practical information needed to design an electromagnetic calorimeter. Generally, the best performance in position and energy resolution is given by calorimeters constructed of high Z materials. However, in practice, there are only a few high Z materials with suitable properties. Uranium, for example, develops an oxide layer, and the dust from machining is somewhat pyrophoric. Tungsten is very difficult to machine to the required tolerances. Tungsten powder is cheap and easy to work with, but can only be compressed to about the density of lead, so it offers no advantage over lead. Notice that the critical energy for tungsten is actually a little higher than for lead, so tungsten offers no improvement in energy resolution despite its higher density, although the position resolution could be twice as good. In fact, the most widely available and workable material for calorimeters is lead. It is available in pure form, and the machine shop loves it because the cutting fluid they use is ethyl alcohol, because it prevents galling of the machine tools. Usually they have a party in the machine shop afterwards. You just have to hope they don't have the party during the machining. After explaining all of these design considerations, I'm going to flatly contradict myself. Actually, it's not economically feasible to build a energy and position resolution limited calorimeter. Mechanical tolerances for such a calorimeter have to be better than the desired resolution, and this is expensive. Mechanical imperfections, such as gaps and dead spaces, have to be factored in, as well as the uniformity of light collection and the uniformity of the electronics. It is also not economically feasible to build a calorimeter with a granularity on the order of the Moliere radius, which is 1.2 centimeters. To cover the same solid angle as the TBC, we would need from 250,000 to 650,000 channels, which would cost on the order of $25 to $60 million. The granularity is in fact determined by the occupancy for typical events, balanced with the cost of electronics. We can afford a few thousand channels. So if we divide it into 4,800 channels and then look at the occupancy for a typical PP, D-gold, or gold-gold event, we find that the occupancy is about 1 to 2% for PP and D-gold events, and it's about 25% for gold-gold events. Our requirements for physics concerns is that we have an energy resolution in the few percent region at high energies and a position resolution of a few millimeters at high energies and low occupancy. For the final design, the granularity is a compromise between energy and position resolution. So what we decided is to divide the detector up into 4,800 channels with good energy resolution and insert a position-sensitive detector into the towers to provide optimal position resolutions at low occupancy with cheaper electronics and consisting of 36,000 channels. Here are some further geometric details. The barrel-shaped detector is built in modules, each of which weighs about 1 metric ton. There are 120 total modules, each with 2 rows of towers inside and 20 towers in Eta. There are 60 on the east side and 60 on the west side. Notice that the scintillators are machined to point projectively to a nominal vertex at z is equal to 0. Each module slides in on a pair of rails to go halfway into the magnet. The east and west ends of the modules meet in the center line at the 8 equals 0 portion of the detector. The modules consist of stacks of lead and scintillator, 20 such layers. As the shower develops, the scintillator samples the ionization of the charged particles produced in each layer. The light output is collected and is proportional to the total energy of the incoming particle. To achieve good position resolution, we insert at the 5th layer a shower maximum detector, which is a position-sensitive ionization chamber. This consists of a double-sided aluminum extrusion, which is capped by 2 circuit boards, one of which has strips in the eta direction and the other has strips in the phi direction. The pitch of these strips is roughly 1.5 centimeters. These strips measure the shape of the shower in the phi and eta directions independently. If the occupation of the detector is low, a few percent of the towers, then this detector can give us precise information about the transverse shape of individual showers, for example, telling us if they are actually closely spaced gamma rays from high-energy neutral pions. Here are the results of beam tests of the calorimeter modules. The upshot of these compromises we have made is that we achieve an energy resolution which is on the few percent level for high-energy gammas, electrons and neutral pions, Ws and Zs, while also achieving a position resolution on the order of a few millimeters. At energies greater than about 8 GeV, the b-tau actually gives better energy resolution than the TPC, which is given by the red line on the graph. Here is a schematic of the star detector indicating the placement of b-tau inside the magnet steel, surrounding the TPC and time-of-flight detectors. Here is the magnet steel, here is the current-carrying coils of the magnet, and here are the projective towers of the Bemc. Here's the TPC, and here's the beamline. Here's a photo with the east pole tip. You can see the layers of the detector. Here's the beamline. Here are the electronics for the TPC. You can just barely see where the time-of-flight system is inserted. And then finally, this copper-colored area covers the electromagnetic calorimeter. Blue is the magnet steel. And here is a rare photograph of the interior of the star magnet without any detectors installed. This is the magnet mapping apparatus. This is me sitting on the rails, and these, if you'll notice, is a rail system which allowed us to insert the electromagnetic calorimeter modules from each end. Note these gaps between the current-carrying coils of the magnet. This allows us to bring the light fibers out from the interior of the magnet to the exterior of the steel to the photomultiplier tubes. Please note the rail system on the top of each module. Each module slides into the magnet on a pair of rails and a system of ball bearings. There is a slight gap in the phi direction between each module, resulting in a dead space that is approximately equal to 1.5 centimeters out of about 23 centimeters in width. There's also a dead area at z is equal to 0, or at 8 is equal to 0, as well, where there's an approximate plus and minus 5 millimeter offset from z equals 0 to the z position of the active volume of the towers. Here's a side view of how the towers are projective in eta. This is a cross-section of the towers from eta is equal to 0 to eta is equal to 1. There's a mirror image of the towers on the other side, east and west, with a 5 millimeter gap at the eta equals 0 faces of the modules, with perhaps a 1.5 centimeter dead area. The light collection scheme deserves some mention. First, we take a flat 5 millimeter sheet of scintillator and we machine 4.5 millimeter deep grooves in it, which are then backfilled with epoxy mixed with reflective titanium oxide. This has the effect of optically isolating the sheets into 2 × 20 tiles. Next, we machine a shallow groove in the shape of a sigma around the edge of each roughly square tile and glue in a green wavelength shifting fiber. When a charged particle passes perpendicularly through the scintillator, the phosphor emits blue light isotropically in all directions. Some of this is captured by total internal reflection inside the plastic scintillator sheets and scatters to the edge of each tile, where it enters the wavelength shifting fiber. The blue light is absorbed by the green phosphor, which then re-radiates green light isotropically within the fiber. Some of this light is then captured by total internal reflection within the fiber and transported out to a clear optical fiber about 1 meter long. This 1 meter clear optical fiber is then threaded through the gaps in the magnet steel and the current-carrying coils to a box containing photomultiplier tubes. We bundle the fibers coming from all 20 layers of scintillator to a single photomultiplier tube. This signal is supposed to be proportional to the electromagnetic energy deposited in the tower. One final signal conditioning is required. It might happen that the photomultiplier tube has areas of low efficiency and high efficiency on the face, and these could accidentally match with positioning of low and high light production from the bundle of 20 fibers. To make the photomultiplier tube response more uniform, we insert a rectangular prism which mixes the light from all 20 fibers in a random way before detection in the photomultiplier tube. This compensates for imperfections in construction and light collection and PMT efficiency variations. Here is a photo of the assembled module from the side. This shows the 20 layers of lead and scintillator, the BSMD layer, the gradual change of projective geometry, and the 20 green wavelength shifting fibers being gathered into bundles and coming out the top, where they are threaded through gaps in the magnet steel and magnet coils and out into boxes of photomultiplier tubes on the outside of the magnet steel. Once the signal reaches the phototubes, it is integrated in a 60 nanosecond window that is timed against the beam arrival every 106.5 nanoseconds. This timing must be performed every time we change energy or species and slightly affects the gain because the integration window can shift slightly. Empirically, we have found that a shift of plus or minus 4 nanoseconds results in a gain stability of better than 2%. However, the gain also decreases from year to year because of other effects, such as aging of the scintillators and photomultiplier tubes. A similar timing is also performed for the shower maximum signal, but the timing is much less critical. A little-known fact is that provision has been made to read out the first layer of scintillators separately, giving us a so-called pre-shower signal. This signal enables us to distinguish between photons or electrons initiating the showers. We implemented this pre-shower for the first few years of STAR, but have now dropped it because of lack of physics interest. The final calibration of BTAU is done by equalizing the spectral shapes of individual towers within rings of constant pseudo-rapidity, then anchoring these values using identified electrons. Using the TPC, we can establish which tracks are pointing at each tower, making certain that they are not hitting the edges. This is the size of a single tower, and this is our pointing ability with track finding in the TPC. Electrons are identified through their specific ionization and time of flight. Their entire energy should be absorbed by the BTAU, giving a peak in the ratio of E over P. We can see this for various rings of eta. One of the first physics topics attacked by the BMC made use of the BSMD subsystem as well. This was the measurement of the neutral pion spectrum. Now, a single tower in the BTAU subtends a solid angle of about 0.05 times 0.05 in eta and phi. The opening angle of a neutral pion decay at, say, 6 GeV is approximately 0.0225, which is a much smaller angle, and thus the closely spaced pion gammas are often contained within a single tower. Nevertheless, the BSMD has strips which are much narrower than that, around 0.007, so the shape of the shower can be examined to determine if the shower is a single or a double cluster. If it is wide enough, then we can decompose it into two showers. We take the total energy in the tower and divide it according to the energy sharing in the BSMD, determine the opening angle, and compute the invariant mass. As you can see, this works very well. With a reasonable set of cuts, we can cleanly and unambiguously identify not only neutral pions, but also eta mesons. What little background remains after combinatoric subtraction is at low mass. This is caused by the large fluctuations in the individual strip energies, accidentally allowing the cluster finder to make a false split of a single cluster into two clusters. The invariant mass of such a false split is biased towards small masses. The physics results are shown here. The reason this result is extremely important is that one of the goals of Starr and Rick is the investigation of spin effects, especially in polarized proton-proton collisions. To this end, we would like to compare our results to those within a framework whose reliability we can trust. Here we see that perturbative QCD, the line with the error bars, describes neutral pion production over 9 orders of magnitude, even at a collision energy of 100 GeV. This gives us confidence to embark on our program of investigating parton distribution functions and other physics questions at these energies. Normally, we would be delighted to find a discrepancy with theory, but in this case, we want to use this energy to explore the spin of the proton and need a reliable theoretical framework to investigate structure functions that we cannot derive ab initio. I want to point out something else. This result is really the first use of b-tau as a trigger for hard collisions. The previous data was taken from high-tower triggered events only, yet results in high-energy pion measurements out to about 17 GeV. We could actually go higher, but the opening angle of those pions is beyond the cluster finding ability in the BSMD. Here I give a similar spectra for charge particles. These spectra come from far more min-bias data and rely on the TPC. You can see that even though there are far more events, the statistics and PT measurements run out at about 10 GeV, not 17 GeV. This extra lever arm to high PT is crucial to a lot of physics topics and is made possible by the fast triggers from the calorimeters, which enrich the data sample in events with hard collisions. Although the polarized gluon parton distribution function is the greatest missing piece of proton structure, the polarized antiquark structure functions can also be improved. Now, it was realized early on in the design of RIC that Starr has access to a channel with very select sensitivity to these functions through the production of W and Z bosons. Consider what happens in beta decay. A U quark turns into a D quark, emits a W+, which decays into a neutrino and a positron. Now, if you distort that diagram in space-time for proton-proton collisions, you can imagine that a U quark in the projectile proton emits a W+, and this selects an anti-D quark in the polarized proton. The W+ is so heavy that it has almost no transverse momentum and decays into a back-to-back neutrino-positron pair. In our detector, we expect a very clean event topology, simply a single high-energy electron with nothing else around it. The backdown for this would come from two back-to-back jets from the hard scattering of quarks, with one of the jets lost down the beam pipe. How can we use the calorimeter to distinguish between these two events? First, we need a precision measurement of the electron energy. Now, for extremely high energy electrons or positrons, we have a problem with the TPC. The measurement of the sagitta, or curvature of the track, is not good enough to determine the energy. In fact, on the right plot, we divide the energy we measure in the calorimeter with the momentum measured in the TPC, and we can just barely distinguish the charge sign from the curvature. In this measurement, the precision of the electron energy is of crucial importance, and the accuracy can be double-checked by measuring the invariant mass of electron-positron pairs to give the Z mass. But the calorimeter can drive down the background due to hadronic processes by examining the topology of the event as well. Firstly, if the energy is deposited by an electron, then it emits 95% of its energy into a cylinder of 2 molare radii or less, or about 2.5 centimeters. This means that the maximum number of towers that can share the energy is 4 if it happens to hit the corner where 4 towers meet. We then make the stringent requirement that at least 95% of the 4 by 4 cluster around this hit is contained in the 2 by 2 cluster. Similar arguments can be made about the isolation of this electron from fragmenting hadrons in the area. We can make another topological cut requiring no energy in a cone of typical jet size around the isolated electron. These two cuts give many factors of enrichment for electrons over hadrons and drives down the background. This physics result is another major star decades-long effort that makes heavy use of the calorimeter. Here are the latest results, which you see allow a clear choice among the many proposed models and therefore a shape of the polarized C-quark parton distribution functions. In conclusion, I would like to summarize the purpose of the star barrel electromagnetic calorimeter. It is a cylindrical detector which nominally covers the same solid angle as the time projection chamber. It is designed to detect electrons, photons, jets, Z, W, and neutral pion decays. It is designed to trigger on events which produce those listed particles via different high-energy topologies, for example, as single particles with a high energy, or as large amounts of energy located in sectors, or back-to-back in azimuth. It provides energy resolutions on the order of 5% and position resolutions of a few millimeters. It contributes to the quality of the vertex by helping to determine which tracks come from which vertex in multi-vertex events. Finally, I would like to mention that it is used in approximately 10% of star papers and is critical in about 80% of star spin results, mostly jets, W, and Z physics. Thank you for your attention.